All right, AP Chemistry, we are in Unit 2 reactions. We're moving on to Lesson 6. It's a concept called empirical formulas. Another plural of formulas is formulae. You might see that occasionally. It's kind of an old-fashioned, archaic term, but it's still, you'll see it from time to time. It's just another way of saying formulas in the plural. All right, so this is going to take a little time to understand. It's a lot of steps, but I'll say none of them is that hard to understand. It's just a lot of steps that you have to get used to doing in sequence. Okay, so this is going to take a bit of work. All right, so some of you will pick it up quickly, some of you don't pick it up as quickly, and again, to those of you that don't pick it up quite as quickly, it's just a matter of time. It's just a matter of you doing it the number of times that you have to do it. How many times your neighbor or partner does it is not what you have to do. You have to focus on what you need to do. So let's go ahead and learn what empirical formulae are and what they're used for. So an empirical formula is the lowest ratio of atoms in the formula of a chemical compound. The molecular formula is the formula of the actual compound molecule or formula unit. So here are some examples. If the molecular formula is C2H4, you kind of reduce it like a fraction, or you can think of it in math like factoring a number out. So it becomes CH2. You have 2 hydrogens for every 1 carbon in C2H4. So the lowest ratio of carbons to hydrogens is 2 hydrogens for every 1 carbon. That's CH2. B2H6. See if you can do this one. Well, there's 6 hydrogen, 2 boron, so that's a 3-to-1 relationship. There's 3 times as many hydrogen as boron, so you can reduce that down to BH3. How about this one? There's sugar. We used that in the last lesson. So what can you factor out of that? Factor a 6 out. By the way, when you factor the 6 out, you don't have to write it out in front like you do in math class. So it's CH2O. So you have twice as many hydrogen as you have either carbon or oxygen. Let's do one more. H2O. What would that be? Well, that's the molecular formula for water. It's also water's empirical formula. You can't reduce H2O down anymore. It's like a reduced fraction. You can't do anything else to it. So the empirical formula and the molecular formula can be the same formula. The empirical formula is the formula of a chemical compound that shows the smallest ratio of elements. That's what you saw on the last slide. The molecular formula is the actual formula of the compound. So we're repeating that to be sure this is a clear concept. So what is the empirical formula for butane? C4H10. See if you can do that one. So this is like reducing a fraction, divide through by 2 to obtain C2H5. This is the empirical formula for butane. There is no actual molecule with the formula C2H5, but this shows the simplest relationship between the number of carbon atoms and hydrogen atoms. CH4 cannot be reduced, so CH4 is both the empirical formula and the molecular formula for methane. So what is an empirical formula used for? An empirical formula is an intermediate, a middle step that takes laboratory measurements and uses these measurements to determine the molecular formula of a compound. So you start off with a laboratory measurement in grams. There's other ways we can measure laboratory output, but in this case we're talking about grams. We then get from the grams to moles. We convert grams to moles because formulas and chemical equations only understand numbers of particles, numbers of moles, numbers of molecules. So we convert from grams to moles just using the molar mass that we've done 100 times by now, and you'll do 1,000 times by the time you're done with this class. So from the empirical formula, we can then figure out the molecular formula. That's the actual formula of the compound. Again, we're really not interested in empirical formulas. We're just using them as a stepping stone to get from the grams that we measured in the lab, which we can then convert to moles, of the substance, we have to know what the substance is, to molecular formula, which is the actual formula of a compound. Using laboratory techniques, you can determine the number of grams of product in chemical reactions. Using the grams of products, you can compute moles and then the empirical formula. So, decomposition reaction is a reaction where a compound is taken apart and broken into its elements. So that's one of the 5 basic types of reaction, which we'll talk about at a later time. But at this point, this is what a decomposition reaction is. It's one in which the compound is broken into its elements. An example is silver oxide is broken into silver and oxygen. By measuring the mass, grams, of Ag and O produced, then converting to moles, we can determine the empirical formula. So example, a decomposition reaction produces 1.651 grams of silver and 0.1225 grams of oxygen. What is the empirical formula of the AgO compound that was decomposed? So compute the moles of Ag. Again, every time you're dealing with a chemical formula, a chemical compound, a chemical equation, it's got to be in moles. Chemical equations, chemical formulas don't understand grams. So it's just a molar mass conversion like we've done a lot of times before. So 1.65 grams of Ag, there's the molar mass conversion for silver. That never changes. If you need to use the molar mass conversion for silver in another problem, it's exactly that same. Of course, remember, you can flip it. It depends on which thing you want to cancel. In this case, we want the grams of silver to cancel, and that gives us 0.0153 moles of silver. We do the same thing now for oxygen. We use the molar mass of oxygen. This is a single oxygen atom now, not an oxygen O2 molecule. 1 mole of oxygen for every 16 grams of oxygen. You get that off your periodic table. And now that's the conversion factor, and now you just multiply through, cancel, and you get 0.0077 moles of oxygen. So these are the grams that we measured in the lab. That's our world. We can measure things and weigh things in grams. Then we use the molar mass translator, and from those two things we can get the chemical world. It's something that the chemical equation or chemical compounds understand, which is numbers of particles, numbers of moles. All right, so there's the same question right there. So create a ratio of the number of moles for each element you obtained. Place the smallest number of moles you computed on the bottom of the ratios. So you'll see where this is going in a minute. So for silver, we figured that we had 0.0153 moles of silver, and we had 0.0077 moles of oxygen. So of those two numbers, the oxygen number is the smallest. So we put that on the bottom of that ratio. And when you do the math on that, you get 1.98. That's approximately equal to 2. So we are trying to get a whole number here for our subscript. So 1.98 is close enough. What's close enough? 1.95 to 2.05 would definitely be close enough to where you can just round it to 2. Remember, you have experimental error here, and so you're going to have some rounding error. All right, now for the oxygen, it was the smaller of the two numbers of moles, so you simply put it over itself. So for the smaller number of moles, it's always going to be that number of moles over itself for the smaller one. And so we get 0.0077 over 0.0077. That gives us a ratio of 1. So the ratio for the smaller number of moles is always going to turn out to be 1. So what this is saying is we have 2 silver atoms for every 1 oxygen atom. Remember, Dalton said we had to get this into whole numbers, so we just did that. So multiply the number obtained in the last step by whole numbers, 2, 3, 4, until you have a whole number. Note, if the numbers are very close to a whole number, about plus or minus 0.05, what I just said, it can be rounded to the nearest whole number. So the figure 1.98 for silver is close enough to 2 to round it. it is not necessary to perform the multiplication here. In other words, we already had whole numbers. We had 2 for silver and 1 for oxygen, so we don't have to do this step. In the next example, you'll need to do this step. So Ag is 1.98 times 1, which equals 1.98, which equals approximately 2. And oxygen, in other words, the number we're multiplying by is simply 1. You don't have to multiply by 2, 3, and 4. Oxygen is 1 times 1. So again, it's the ratios that we came up with on the last step, 1.98 and 1. You just multiply by 1, and you get whole numbers in both cases. So you don't need to go any further than that. So place these numbers as subscripts of the elements. This is the empirical formula. So it's Ag2O. So you have 2 silver atoms for every 1 oxygen atom. So stop, pause, go back and watch that a second time so you understand this process. Okay, let's see another example, and it'll become a little clearer after you see a second example. So here we're going to do a decomposition reaction with selenium bromide, Se and Br. And you're given a number of grams of selenium and a number of grams of bromine that come out of that decomposition reaction. So there's the reaction there. You take SeBr and you break it into Se and Br, and you're told how many grams the Se weighs and how many grams the Br weighs. So compute the moles of Se and Br using the molar masses. So there it is, 1 mole of selenium for every 78.96 grams of selenium. You get that right off the periodic table. You multiply by the number of grams of selenium that you came up with in the lab, and you get 0.018 moles of selenium. So we need to convert the moles to use a chemical formula or chemical equation. Here's the same computation for bromine, 6.472 grams of bromine. The molar mass of bromine is 1 mole of bromine for every 79.90 grams of bromine. You get that off your periodic table. So you have 0.018 moles of bromine. So grams is our world. That's what we measured in the lab, the number of grams of selenium and bromine. You use the molar mass translator, and you come out with a number of moles that the chemical equation and chemical formula speaks in. Okay, so here's the problem restated. So now you create a ratio. Now you're going to see this concept better than the last problem. Create a ratio of the number of moles of each element you obtained. Place the smallest number of moles you computed on the bottom. So we had 0.018 and 0.081. So we're going to create for bromine, that was the 0.081. So we write that, and then we place the number that we had for the selenium beneath it, because selenium was the smaller of the two. Now we do the same for the selenium. And again, the smallest one is always going to be its number of moles over itself. So you create the ratio, it's always going to be 1 for the smaller number of moles. So now we just have to do a little math on the bromine. So divide the top number by the bottom number. So for bromine, 0.081 divided by 0.018 is 4.5. And for selenium, of course, the smaller one is always going to be a ratio of 1. So it's 1. Now, here you notice that we don't have a whole number for bromine. Okay, you can't have Br 4.5 with a subscript of 4.5. We're not allowed to do that. Dalton says they have to be whole number ratios. So the way you deal with this is you just multiply through, as we said on the earlier slide. Let's go ahead to the next slide to do this. So multiply the number of moles by whole numbers 2, 3, 4 until you have a whole number. You don't have to do it forever, just do it until you get a whole number. So here's bromine. 4.5 times 2 equals 9. Hey, right away on the first try, we got a whole number. So 9 is the number for bromine. But don't forget you have to multiply selenium also by 2. So you had selenium 1, you have to multiply that by 2. Remember, it's a relationship of number of selenium atoms to bromine atoms. And so you get a 2. So now you have 2 whole numbers, and those become the subscripts for each of those elements. So place these numbers as subscripts of the elements. This is the empirical formula. So it's Se2Br9. So again, go back and re-watch that a couple of times even, and think about it, okay? Try to gain a little more insight, a little more depth to your knowledge. Okay, so now we've figured out how to compute an empirical formula. Now comes the good part. We're going to figure out how to use that to figure out the molecular formula, the actual formula of a compound, without even knowing what it is, okay, what that formula is in advance, okay? So here we go. Okay, so now comes the good part. We're going to see how this works. So a hydrocarbon is a compound made of carbon and hydrogen. A combustion reaction burns a hydrocarbon with oxygen and produces carbon dioxide and water, and has the general formula: some CH compound plus oxygen, O2 molecule. You light a match to that. Once you get the fire started, you can put the match out, and that's going to produce carbon dioxide and water. So our goal here, and I'm going to put this little tag down at the bottom of just about every slide. Our goal is to determine the chemical formula subscripts of an unknown compound. In this case, it's that hydrocarbon compound. It's CXHY. We don't know what those X and Y are now. That's what we're going to figure out, and figure out what the chemical formula is for that compound. So I don't want you to lose sight of the big picture with all the details that we do. That's what we're trying to do, is find out what the actual molecular formula of that compound is. So here's our example. Combustion of an unknown hydrocarbon produces 5.72 grams of CO2 and 1.17 grams of H2O. Determine the empirical formula of the compound. So a couple things to notice. What we're getting is the product of that reaction, the carbon dioxide and the water over on the right side of the equation. And we're getting it in grams. That's something that we can measure in the laboratory and put on a scale and measure. So that's what we have to start with, and we've got to work backwards to figure out what the formula is for that CXHY, at least the empirical formula at this point. So analysis. In the lab, we burned the unknown hydrocarbon in a combustion reaction and weighed the number of grams of each of the products, CO2 and H2O. So that's shown up there above. So this is what we learned in the lab. 5.72 grams of CO2 was produced and 1.17 grams of H2O was produced. And that's something we can weigh and measure. That's what we do in the lab, and that's all we can do in the lab at this point. So now we're going to have to do some pencil to paper work to figure out the rest of it. So we use the molar masses for CO2 and for water, you've seen these before, to figure out how many moles of CO2 and water we have, because chemical equations and chemical compounds only speak in the language of numbers of particles. Okay, numbers, I need a senior for every 2 juniors. I don't care what they weigh. I want one senior for every 2 juniors. Here you're going to want to know numbers of particles here, numbers of moles. So our goal is to determine the chemical formula subscripts for an unknown compound. Okay, so there's our problem restated. So now we convert grams to moles using molar mass conversion. You've done that quite a few times in this class. So 5.72 grams of CO2 times the molar mass of CO2, 1 mole of CO2 for every 44.01 grams of CO2. Remember, you have to put it in the order top and bottom that will make grams of CO2 cancel out and moles of CO2 appear in the final answer. And what we get for that is 0.13 moles of CO2. Now you do the same thing for water. We measured 1.17 grams of water in the lab from this reaction. Molar mass of water, 1 mole of H2O for every 18.02 grams of H2O. You need grams on the bottom, grams of H2O on the bottom. Cancel with grams in the 1.17 grams of H2O. And that gives you moles of H2O. And so that's 0.065 moles of H2O. So our world is the world of grams. That's what we measured in the lab. We use these translators called molar mass translators that relate moles to grams, and that puts us into chemical world, what the chemical equation and chemical compounds understand, which is numbers of moles. Okay? So we're ready to move on now. We know the number of moles of CO2 that came from this reaction and the number of moles of water. So our goal is to determine the chemical formula subscripts for an unknown compound, the CH compound up in the upper on the left side of the equation. So we look at the flow of carbon. So notice that there is 1 mole of carbon for every 1 mole of carbon dioxide. Again, think of the carbon dioxide as a bicycle. For every bicycle, 1 bicycle you make, you need 1 bicycle seat. And think of the oxygen as the wheels. For every 1 bicycle you need 2 wheels. So for every carbon dioxide molecule, you need 1 carbon atom and 2 oxygen atoms. For every 100 carbon dioxides you make, you need 100 carbon atoms and 200 oxygen atoms. For every 1 mole of carbon dioxide molecules you make, you need 1 mole of carbon and 2 moles of oxygen. So it's just those relationships, those ratios that we talked about. So there's 1 mole, because there's no subscript beneath the C, it means it's a 1. So there's 1 mole of carbon for every 1 mole of carbon dioxide. Be sure you understand that. So, where did all of that carbon have to come from? There's only one place it could have come from. All of the carbon in the CO2 molecule must have come from this hydrocarbon compound, this CH compound. There's no other place it could have come from. There's no other carbons in the equation. So our goal is to determine the chemical formula subscripts for an unknown compound. Okay, so here we go. This is the slide that you may want to watch a few times. Down on the bottom, we're going to do the stoichiometry equations like you've done in the last couple of assignments. And then we're going to do the pathway. We're going to show how this flows. Kind of like the graphic organizer where we drew the arrows. We're going to do that in the pathway. So we said we're starting off with 5.72 grams of CO2. That's up in the problem. That's stated in the problem. Now we need to do the molar mass, which we did on the last slide, but we're going to do it again, put it all into one equation here. So that's the molar mass of carbon dioxide, 1 mole for every 44.01 grams of CO2. And up above there where that arrow is pointing, that means you have 0.13 moles of CO2. Now, how many moles of carbon do we need for every mole of CO2? We stated that earlier. You need 1 mole of carbon for every 1 mole of CO2. So we're going to put that as a ratio, 1 mole of carbon for every 1 mole of CO2. And that's going to give us 0.13 moles of carbon. So there we go. So you know how many moles of carbon we produced. Now, where did all that carbon have to come from? It had to come from over here. So that means we had to start off with 0.13 moles of carbon. You cannot create or destroy molecules. You cannot create or destroy atoms. You cannot create or destroy moles. So if we ended up with 0.13 moles of carbon on the right side, we had to start off with 0.13 moles of carbon on the left side. So now we're going to go ahead and we figured out our subscript for X, and it's 0.13. Okay, now some of you are thinking, hey, you can't have a decimal number there. You're right. Dalton says we have to have whole numbers. Okay, we'll deal with that later. But first we're going to figure out what the subscript for hydrogen will be. So study this, okay? Even go back and replay the video if you need to. Study how we got this. Okay, so now we're going to do it for the hydrogen. So we start off with 1.17 grams of H2O. All right, so there's the pathway, there's the stoichiometry. Now notice that the hydrogen that's in water, H2O, could have only come from one place, and that's from the hydrocarbon over on the left. So whatever number of moles of hydrogen we have on the right in the water molecule, we'll have to have started with that same number of moles of hydrogen over on the left. Okay, so there's the molar mass conversion for water, 1 mole H2O for every 18.02 grams of H2O. And there you go. That gives you 0.065 moles of H2O. We figured that out on the previous slides. Now, to make a bicycle, you need 2 wheels. To make a water molecule, you need 2 hydrogens. If you want to make 2 water molecules, you need 4 hydrogens. If you want to make 1,000,000 water molecules, you need 2,000,000 hydrogens. If you want to make a mole of water molecules, you need 2 moles of hydrogens. You need twice as many hydrogen as water molecules. So there's our conversion. There's 2 moles of hydrogen for every 1 mole of water. So that's going to give you 0.13 moles of hydrogen. So we come up here, and that 0.65 doubles to 0.13, and that's how much hydrogen we have. We have 0.13 moles of hydrogen. So now we're going to come across. The 0.13 goes there, and it replaces our Y as a subscript, and now we know our subscripts for carbon and hydrogen. So now we're going to convert them into whole numbers, which they have to be. So here's the same question. So there we have what we said we had, C.13, H.13. So we're going to create a ratio. We must have integer values for the subscript of the chemical formula, so we convert the ratios below. You put the smaller of the 2 on the bottom. Well, they're both the same number, so it doesn't matter which you put on top, which on bottom. So 0.13 hydrogen over 0.13 carbon gives you a 1-to-1 relationship. So instead of writing that CH as a 0.13, you write it as a 1, 1. So the empirical formula is CH, C1, H1. All right, so that's your empirical formula. Now that might also be the molecular formula, but I'll tell you in advance, it's not. There's no such molecule as a CH molecule. It's simply the lowest ratio of carbons to hydrogen. So the empirical formula of a compound is the lowest whole number ratio of elements. The molecular formula of a compound is the actual chemical formula of the compound. In the previous problem, we found an empirical formula for a hydrocarbon compound, and there it was, CH. There is an infinite possible number of molecular formulas that could have this empirical formula. Think about it. CH is one, C2H2 is another, C3H3, C4H4, C5H5. All of those compounds, if they existed, would have an empirical formula of CH. It's a 1-to-1 relationship. So, and so on. So what we're going to try to find out is what is the actual molecular formula for this hydrocarbon. So how can we know what the actual molecular formula is if we know the empirical formula? The answer is, if we know the molar mass of the compound, we can derive the molecular formula of the compound from the empirical formula. Now your first reaction might be, how can we figure out molar mass if we don't even know what the compound is, right? When we figured out molar masses in this class, you had to look at your periodic table and how many moles of C did you have and how many moles of H did you have, but you don't know that. So I'm just going to ask you to accept as a matter of faith right now that it can be figured out. You can figure out the molar mass for an unknown compound. That's really a matter of laboratory technique, and it's not something I want to go into now because you got enough to deal with this subject right now. But just accept that you can find out the molar mass of an unknown compound. It is possible to do that. So we're going to move on with that fact and calculate our molecular formula. So example, it is determined that the molar mass of the CH compound that we're working with in this example is 78.11 grams. What is the true molecular formula of the compound? So note, we will leave the question of how molar mass of an unknown gas is determined for another discussion. Okay, that's what I just said. Don't worry about how they know that. There is a way to know that. Okay, so it is determined that the molar mass of the CH compound from the previous problem is 78.11 grams. What is the true molecular formula of the compound? So we compute a scaling factor that we just give the letter N. Based on the ratio of the molar mass, that's the 78.11, of the actual gas over the molar mass of the empirical formula. That's called the empirical molar mass. So what is that? So there's the formula. The actual molar mass, 78.11, over the empirical formula molar mass. So what is that? So we determined the molar mass is 78.11. So the empirical molar mass, you simply take the empirical formula CH and you calculate the molar mass the way you normally would from the periodic table. Carbon is 12.01 grams per mole. Hydrogen is 1.01. You have one of each of those. So that adds up to 13.02 grams of CH, and that's called the empirical molar mass. Again, there's no such thing as a CH molecule, but this is going to help us to get to the actual chemical formula. So multiply the subscripts of the empirical formula for one for C and one for H by the factor n. So let's first compute the factor n. There's the formula again. So it's 78.11 grams is the molar mass over the empirical molar mass that we just computed is 13.02, and that gives you approximately 6. So that's the factor. So that means we're going to take the empirical formula CH, and which is really an empirical formula of C1H1, and we're going to multiply those subscripts by 6. So the actual molecular formula of the actual real-world molecule is C6H6. Okay? And that's how you use empirical formula to figure out what is the actual formula of the actual compound that we just burned in that combustion reaction. It's a lot. So here's what I wanted you to get on this first one. Just kind of understand the process. If you didn't understand it all, that's okay. We're going to do another example. And then each time you work a problem, try to understand one more step than you knew before. Don't worry if you don't understand the whole thing the second time through. Try to understand just one more step each time you do a problem. Maybe you get to where you can do 2 or 3 steps that you learn in each time you do it. But set a goal of one step. I know one more step than I knew before I did this problem. That means you might need to do 5 to 10 of these problems. All right? Well, you're going to do one more here. So here we go. All right. So same essential problem, except I gave you a different number of grams of CO2 and of H2O. Okay? Otherwise, it's exactly the same problem. So see if you can follow the steps this time, maybe a few more than you could before. So there we go. We're starting with 33.01 grams of CO2. And we're going to have a pathway with arrows, and then we're going to have the stoichiometry. So the first step is we take our 33.01 grams of CO2, multiply by the molar mass conversion, the conversion factor for molar mass of CO2. Again, you wanted to set it up so the one on the bottom is the one that makes grams of CO2 cancel out. So we did that there, and moles of CO2 is on top. We need to be in moles in order to work with a chemical equation. So there we go, and that gives you 0.75 moles of CO2. Now we see the same relationship we saw last time. There's 1 mole of carbon for every 1 mole of CO2. 1 bicycle seat for every 1 bicycle. A mole of bicycle seats for a mole of bicycles. Okay, so it's a 1-to-1 relationship. So we're going to go ahead and do that, and now we know we have 0.75 moles of carbon. Now, so where did all that carbon have to come from? It had to come from the hydrocarbon over there on the left. So that's got to be 0.75 moles as well. It's the only place we got the carbon from. And that puts us up here, and that changes our subscript to 0.75. Okay, now we're going to do the same thing for the hydrogen. And we're going to do it exactly the same way as last time. Okay, now we're going to do the same thing to figure out the subscript for hydrogen. So the problem tells us we collected 13.51 grams of water. So now we do the molar mass to figure out how many moles of water that is. And after that calculation, we come up with 0.75 moles of water. Now, our bicycle needs 2 wheels for every 1 bicycle. Our water molecule needs 2 moles of hydrogen for every 1 mole of water. So we do that conversion in our stoichiometry, 2 moles of H for every 1 mole of H2O. And that gives us 1.5 moles of hydrogen. That's how many moles of hydrogen we collected. So now, where did all that hydrogen have to come from? The only place it could have come from is from the hydrocarbon. So that's 1.5 moles there. And we can replace that as our subscript. So now we have our subscripts, but we have to get them in whole number ratios. So we're going to do that on the next slide. So this time we actually do have a smaller number than the other one, and that's the moles of carbon. So we have 1.5 moles of hydrogen over 0.75 moles of carbon. And what we find out, that's a 2-to-1 relationship. Twice as many moles of hydrogen as moles of carbon. So that's 2-to-1. So those are going to be the subscripts of our empirical formula. So the empirical formula is CH2. It's just saying that somehow there's twice as many moles of hydrogen as moles of carbon. The actual molecular formula could be CH2. It could be C2H4. It could be C10H20. It could be C1 million H2 million. I mean, it's going to be some 2-to-1 relationship. That's all we know yet. We don't know exactly what it is. Okay, now we want to figure out the actual molecular formula for the actual molecule that we're dealing with here, for the actual hydrocarbon. What is its real formula? So to do that, we need to have the molar mass of the compound. And again, just accept that that can be known without knowing what the compound is. There are experimental ways to determine that. So you're just going to accept that for right now. So the molar mass is 28.06. We've seen that number before when we've done molar masses. You might recognize it. Now we also need to compute the empirical molar mass for CH2. So the one carbon has a molar mass of 12.01 grams, and the two hydrogens are 1.01 each. You multiply those by 2, multiply that by 2, and you end up with a total of 14.03, which is the empirical molar mass for the empirical formula CH2. So now we can just do a simple division problem. There's the formula. It's 28.06 divided by 14.03, which gives us 2. So the empirical formula was CH2, and the molecular formula, the actual formula of the real molecule, is C2H4. You multiply the C, the 1 in the subscript of C in the empirical formula by 2, you multiply the 2 in the subscript of H by 2, and you get C2H4. So that was our goal, was to determine the chemical formula subscripts for an unknown compound, and to do that we used empirical formula as a middle step to get there. All right, there was a lot to this. It's a long lesson. If you will practice 5 to 10 of these, you'll be the world champ. So the only question is, how long is it going to take you to practice 5 to 10 of these? Are you going to put it off and do it over 2 weeks? Then you won't understand it for at least 2 weeks. If you do it soon and quickly, and then do some practice, maybe a week from now, then it'll really stick, okay? It's not a difficult concept, it's just a lot of steps, and you got to realize the difference between the two. All right, so that takes care of this lesson, and we will see you on the next lesson.